We have been tasked to design a simple spar and aerofoil capable of withstanding set, span-wise bending and torsional constraints while optimizing it so as to keep mass to a minimum.
We tested many designs for the shape of our spar, first conceptually using the spreadsheet, then through building and testing our design till failure. One shape that we tried was an I-beam, which held up very well when loading and could withstand large bending forces due to its great second moment of area, but it failed to provide the rigidity needed under torsional loads. In the end, we opted for a rectangular shaped beam which provided both bending strength and torsional stiffness.
In the preliminary design process, calculations are performed using Excel. Firstly, finding the peak moment as if the spar was a cantilever and a point load is acting on the tip, as well as the polar and second moments of area, which are a measure of the structure's resistance to torsional loads and the area distribution around the centre point respectively. These values could be used with the Euler-Bernoulli theorem to calculate relevant values. We found that the maximum deflection is inversely proportional to the second moment of area, and the torsional compliance is inversely proportional to the polar moment of area. We made sure that the values used within the spreadsheet are within the bounds of the wing rib so the spar design could fit in the aerofoil shape. This calculated that the best designs were where the mass of the spar is as far away from the centre as possible to create high resistance to torsion. The only limitation of this design section is that the spreadsheet can only calculate values for rectangular profiles and not structures that are progressively narrower over their length, which will become relevant later.
After designing our spar with respect to the Excel sheet, we made a CAD assembly with the aerofoil and support. We ran load and torsional simulations with the same design. We ran various load values to check if it was correlating with the Excel sheet data. We ran 1G, 2G and 2.5G loads. All the data from the Excel sheet was not directly correlating with the simulations. We had slightly higher deflections and had to redesign parts to increase its strength. The Excel sheet also specified various dimensions that would theoretically work but did not in simulations or in real-life testing.
For our final design, we decided on a rolled spar as it made correctly aligning the sides much easier, which resulted in a more optimal shape. We glued the inside of the joint, which helped maintain its shape when subject to a torsional load, and overall the spar was lighter as we used less tape thanks to the paper joints. Through simulations and our testing of the spar, we also found that it often broke at the root due to the load. To counteract this, we placed a vertical support inside the spar on both sides, but only up to halfway as the stress placed on the spar decreased further from the root, meaning the extra support wasn't necessary. This allowed us to improve the structural integrity of the spar, whilst also keeping the additional weight to a minimum placed on the spar.
By organizing effectively and working collaboratively, our group successfully completed rapid prototype testing and developed a functional design by the third lab session. However, we encountered challenges due to the limitations of the Excel worksheet, which necessitated additional lab testing.